All right. Hello.
Hello.
Thank you all for coming to the History of Diving Museum. It's been a fabulous evening. We got a little bit of a preview from Aquanauts to the Astronauts exhibit that will officially be open on May 20th. So thank you all for coming early. We got some wonderful beverages and some food from Meat, our local eatery. Everybody loves that. Yeah. So for those of you that are not familiar with the History of Diving Museum, we're located in Alamorada at mile marker 83. For those of you that are zooming in and not here in person, we opened in 2005, and for the last, since 2016, we've done a featured exhibit, 2 of them annually. Generally during the winter from January to April, we have an art exhibit, and then the second half of the year, we have a science and history. Right now, Aquanauts to Astronauts. And we try to have different groups come in that may not think of diving. So a lot of hopefully space enthusiasts will now learn about the other side of extreme environments. The History of Diving Museum on the 3rd Wednesday of every month offers this presentation. So come on down. We say don't drive by, dive in. Tonight we have Michael Gernhardt, who is consider him my favorite astronaut because he was a commercial diver first, which gives him that cool factor. And then, oh, by the way, now he's an astronaut because a lot of those skills transition, which is what he's going to teach us about and tell us about going forward. So thank you all for being here. If you're online, go ahead and put your questions in the chat, and Julia will be taking care of those and then coming in and answering those as we go. As he goes through, at different times, if they want to ask questions or hold it to the end, what would you prefer?
Whatever you want. Usually it's cleaner to leave it at the end.
Okay, all right. So think of your questions, hold them, and at the end we'll do we got time for Q&A.
Okay.
All right. Thank you for being here.
Well, thank you, Lisa, and thank you all for being here. I'm starting my stopwatch because in spacewalks you feel about time. So she told me 45 minutes, and then we'll have questions.
And make sure you silence your cell phones.
Okay. Okay, so I'm going to talk about sort of my career path from inner space to outer space and then back with the saturation habitat stuff. And as a teenager, I was really motivated, like many of my generation, with Jacques Cousteau, and they were doing these underwater living experiments. And I started diving really young. I was certified at 12 and was really into the ocean. And at the same time, they were doing tektite, which was an underwater living experiment with saturation. A tektite, if you don't know, is actually an asteroid that lands in the sea, and it forms this like really cool black looking rock. So it's sort of space to sea. And so that really motivated me. And I was starting to get really interested in school, and I wanted to do the most I could with the life I had, both mentally and physically. And so to me, that was to aspire to be an astronaut. And everyone said, well, you have to go join the Air Force. And I decided to do it by way of the ocean. So, but at the time, there was all this fantasy, we're going to have underwater cities and all that. And the reality was different. It was commercial diving. And this thing here is a blow up preventer. And they were called diverless systems, like Hughes Aerospace and Ball. And they were triply redundant and not supposed to fail. But they failed miserably, and they're very complex. So it required commercial divers to work on them. And that actually ushered in the era of saturation diving. I think most of you know what that is, but basically we live in these pressurized habitats on the deck of the vessel at the same pressure that will work in the ocean. And we transfer into this diving bell, which has been overboarded, and you lock out of the bell. And for example, if I was working at 500 feet, if I did a 15-minute bottom time, I'd probably have a 30-hour decompression. But once you're saturated, it takes about a day per 100 feet to decompress. And so if you look at the bottom time you get to the decompression time, this is a smart way to go. So I've lived in these things, very complex. You know, at the depths we dive, you have less than 1% oxygen. And a swing of a few percent in the oxygen is the difference between acute oxygen poisoning and hypoxia. A couple degrees in temperature and relative humidity is the difference between comfort and discomfort. more than that can be life and death, because the thermal conductivity of helium is really high at these depths. And so we actually had these SAT systems built in below decks on these diving support vessels. This one is actually a 12-person saturation system. So think of that as like a space station. And then we had a moon pool that would open up, and then the diving boat would be deployed through that. And these vessels had, they would drop a tension wire, and they could station keep from the accelerometers in like 30-foot sea. So really wild technology. And so I started out as a scuba diving instructor, love the coral reef and stuff, and then welcome to the real world in commercial diving. So this is one of the first jobs I did. And I was a diver and the engineer on this job. And there were these platforms in Peru that had been put in 30 years before with no anodes. So they were falling apart, and the pilings were all out of order and all this stuff. And so we designed these clamps, and we put the clamps on based on the engineering drawings. And then we took this jig down that was like a 2-inch pipe that was extendable. And then there were 2 hinges, and we'd weld the flanges shut and then bring that up and fit a pipe between it. So we actually rebuilt this platform completely underwater. I learned a lot about how you plan a dive and how you want to cheat in every way you can to make it better on the bottom and have plan A and plan B. And you can't get those skills. And here doesn't matter where you went to school or what it's what you can do on the end of the hose. We did other jobs with hyperbaric welding where we had to design these multi-piece habitats, and we'd install a ring on the leg and then take each piece down and hang it on the ring and then pull them together and install flanges and then go inside and weld in the dry environment. And to do code quality welding, you have to be dry, because if you do wet welding, the water quenches the weld so fast, you get hydrogen embrittlement. And then this is a fun thing, flanging up pipelines where they're slicing back and forth. You can lose a finger really easy. And sometimes you're doing this like almost zero visibility. So I'm lucky I had all my fingers and I'm still alive. So because the expensive saturation diving was so much, and I'm going to talk about dogs here in a minute. And the oil companies didn't like divers because we'd come onto their barge and get things wet. And divers tend to be kind of cocky about stuff. It's just comes with the job. So they tried to invent these robots to do what we were doing. This is called the Mobot that British Petroleum developed. It lasted like a week and didn't do anything. This is the Trove. And the salesmen were selling these things that they could do the same job as a diver could. I made more money in depth pay rescuing these things. And then, as you see in the museum, then I worked for Oceaneering, and we invented this gym suit called the gym suit. So it's 1 atmosphere inside, so you can go down to 1,000 feet and not have to be compressed. But you have to work with these pressure balanced joints and these end effectors that are like vice grips. And so you really have to design the equipment to be serviced by the suit. And you can see these valves are all within the work envelope of the suit, but you're so limited because you walk. And so that didn't last long. And then we tried the jet gym, and you almost need a stopwatch to see how long that lasted, because it had a jet pack on, but you had to pull your hands inside to drive with joystick. And it just didn't work. And so a British guy named Graham Hawkes invented the WASP suit. And I talk about a Darwinian evolution of subsea work systems. This is the only one that's still working now, but you actually have thrusters and you fly it with your feet, and it leaves your hands free to work. So it's a very good system. Here's another one. This is called the arms belt. And you're at 1 atmosphere inside, and we invented this force reflecting manipulator with General Electric that was so sensitive that you could thread a shackle pin. And I'm looking at Hank here, who knows all this stuff, but it's hard to thread a shackle pin even with your bare hand. This arm could do it, but it was very expensive and it kept breaking down. It was so good and so fast. A friend of mine even caught a fish with it. But I always said, if you want to go fishing, you'd buy a $75 fishing rod, not a $4 million manipulator. So we then worked with International Submarine Engineering and came up with this dual hydra system. These are relatively simple manipulators, very robust. And we changed the design of the task so that you could do it. So instead of threading the shackle pin, we would have a wire on a pelican clip. And so all the ROV had to do was come down and grab it and pull it, and that would release the lift line. And watch closely here. There's something pretty cool about to happen. So there's the blowout preventer. This is 3,500 feet.
Wow.
And that's a sperm whale. And he was attracted by the noise and the tether of the sub. So he's just kind of chilling out.
Wow.
Didn't get too excited. But you never know what you're going to see in the ocean. Hopefully you don't see this in space. Anyhow, so we redesigned the task, and I'm not going to bore you with all this detail, but we did these completely subsea production facilities that were serviced by an ROV. And instead of having all the valves very deep inside, we ran pipes out to a single panel where the ROV could dock and then turn the valve. And it's, you know, what we called it interface engineering. And so actually the assembly and maintenance of space station has its roots in the things we learned in commercial diving. And I founded the company Oceaneering Space Systems in 1987 to transfer this subsea technology to the space station. And at NASA, it was very polarized. There was one group that said robots could build all this stuff. And then another group led by Gene Kranz, the famous Gene Kranz, he called these robots the golden monkey. He goes, I don't want a golden monkey up there. So anyhow, I started this company to do human and robotic stuff and then life support and hyperbaric physiology. And this is an interface that we invented for subsea. It was called the conical interface. And basically all you had to do was dock the ROV to that, and it would turn, there was special tooling inside. And so I sort of revisioned that as the micro conical interface. And there's hundreds of these all over the space station. And that allows robots to change out these orbital replacement units. So anyhow, then got to be an astronaut. And people always ask me, what's the difference between it being a diver and an astronaut? And the first one is how you get to the job. As a diver, if you're taking a boat or a helicopter out on the space shuttle, we spent years training to learn all of this stuff. And this is just a view of the cockpit. It's got 3,000 switches and circuit breakers that you really have to know like the back of your hand. And I always remember this on the first sim that I did, the chief of the astronaut office was in there. His name was Hoop Gibson. And he said, Mike, you did pretty good, but always remember there is no problem that can happen with the space shuttle that you can't make worse. Because we have 3 levels of redundancy. And if you see an alarm that the auxiliary power unit number 1 went down, but you reach over and you shut down number 2, you just killed yourself. So the training was amazing. And then I got assigned to my first crew, and this is appropriate here. So the commander his call sign was Red Dog, and so he christened us as the dog crew. So I said, we have a dog here. And, to build a team, he gave everybody a dog name, with the only condition that you couldn't like your name. So, you know, I wanted to be like Dogfish, and I was Underdog. The rookie. And then this guy was in the Army, Jim Boss, he's Dogface. This is the pilot Cujo, who is very mild mannered. So Cujo. And this guy was really kind of a computer geek, and Dave was debating whether to call him Goofy or Pluto, but he got the name Pluto. Here we are, one of the launches. You get all dressed in, you have a parachute on in case you have to bail out. And it was actually raining, and we didn't think we were going to launch. And then right in the middle of the launch window, it cleared up, and there we go. So we light the main engines, and then when the solid rockets on the side ignite, you're going somewhere because you can't shut those things off. So here you see it's going through Mach 1. And then shortly after that, we separate the solid rocket boosters. And I'm going to show you a clip from the inside. It's quite a ride. And when they separate you, there's pyros that fire. Here we are. And, oh man, you're just shaking and vibrating. And after you get rid of those, it sort of smooths out. We call it like an electric glide. And in the last 2 minutes, we're throttling back, and you have 3 Gs through your chest. But then you get up there and you float out and you look out the window, and it takes your breath. And you know, we launched. This is the Bahamas, and you're like, wow, I'm here floating in space. It's really amazing. And we launched during a series of hurricanes, and so this is a hurricane from space. And so in the first mission, I deployed this solar science research satellite called Spartan. And it was supposed to do its mission and come back and then park itself in an orbit normal position, and we'd rendezvous and grapple it with the arm. I could see from 10,000 feet out that it was spinning. And so we get up there and it's spinning in all three axes at way above the rates that were certified to grapple it. And so Dave Walker was flying the shuttle trying to match the rates, but we got low on prop. And so he said, underdog, go for it. And so I reached out with the arm, and right as I grappled it, the arm hit what's called a singularity. The alarm went off, but we got it. So he always used to say this saying, maybe not politically correct, but he said, it's a fine line between shit and shit hot. And I bumped that satellite, forever in history, that would be Mike Gernhardt. Anyhow, so then we did another one called the Wake Shield, and then I did a really formative EVA where we evaluated all the tools and techniques that we would use to assemble and maintain the space station. There's a backstory about this picture that I probably don't have time to tell you, but I had dislocated my shoulder right before the flight, and anyhow, it's funny. We launched like a week later, and they were asking me to wave. My shoulder was so painful, I could only raise my arm that far. Anyhow, so let's talk about decompression. You guys are mostly divers, I assume, but so we have to denitrogenate. So we're saturated right now. As you sit in this room, you're saturated at 14.7 psi, and we want to work at a lower pressure of the suit so that the delta pressure for closing your hands and working is less. So the suit is at 4.3 psi. And we have to decompress to do that. There's lots of other stuff that we deal with in the suit, but in terms of decompression sickness, the character of altitude decompression sickness is much different than diving. This is a plot that shows the percentage of type 2 DCS from all DCS reported. In commercial diving, it's about 40%, recreational, it's close to 50, scientific's even more. And then you go over and you look at Brooks Aerospace and our NASA test, it's very little type 2 DCS. And the reason for that is that we pre-breathe oxygen to get rid of the nitrogen. And it turns out, here's the nitrogen elimination curve. You actually eliminate half of your nitrogen in 30 minutes. But more importantly, your brain and spinal cord have a very fast half-time because the blood flow is so high. So the half-time with the brain and spinal cord is only like 5 to 10 minutes. And so as we pre-breathe this oxygen, you totally undersaturate your brain and your spinal cord. So it's very unlikely to get type 2 DCS. So I had done my PhD on basically a new decompression model. And so when I came to NASA, as we were getting ready to build a space station, they asked me to lead this whole development to do a new decompression procedure that would be at least as safe as the 4-hour pre-breathe we did on shuttle, and hopefully cut the time in half. And for the shuttle pre-breathe trials that they went to flight with, they had 25% DCS on the ground. And 5% of that was type 2 or symptoms that would terminate EVA. Unfortunately, we never got DCS on the shuttle. And the reason was that for operational reasons, we actually stayed at the 10.2 PSI stage much longer than the ground trials. But anyhow, as I started this research program, there was 2 sets of data that showed that we might be able to reduce decompression sickness. One was the Air Force did this experiment where they did 10 minutes of exercise at 75% of your max VO2, and they had about the same DCS risk in 1 hour pre-breathe with 10 minutes as our 4-hour pre-breathe. So the notion is exercise can speed up the blood flow and nitrogen elimination. And there's another series of experiments that Dick Van and the guy named Mike Powell did. And the notion was when you walk in 1G, you have these lower body musculoskeletal stresses, and you can create a phenomenon called tribonucleation that forms these nuclei that can later turn into bubbles. So we combine the exercise with the non-ambulation, and we did these trials. When they did the shuttle trials, they had 25% DCS. And they said, well, I don't know, go to flight. And so the first thing I wanted to do was define what acceptable DCS risk was. And it was interesting because the diving community felt like it should be 1 to 5%, primarily because there's a lot of type 2. The Air Force thought, hey, less than 40% is fine. And so I couldn't get anybody to agree. And at the time, NASA did not have a DCS disposition policy. And there was a friend of mine who was a suit tech that got bent and he reported it and they grounded him. So you think an astronaut's going to report when he has DCS? No. And so I forced us to establish a DCS disposition policy. And that was if you have one type 1 DCS incident, you can go EVA in 72 hours. If you get a second one on the same mission or a type 2, then you're out of the rotation. So with this policy, I basically applied that to the whole assembly and maintenance of space station. It was 484 EVAs, and I subjected it to the probability, the highest risk you could have, where there's always 2 of 3 crew members available to do spacewalk. And that turned out to be 21%. And so I said, does anybody think it should be more than that? No. And so then we said, why should it be less? Well, we don't have hyperbaric chambers on orbit. When we get bent out on the space station, it can take 15 minutes to get back to the chamber. At the time, PFO, you guys all know what PFO is? Raise your hand if you know what PFO is. It's called a patent foramen ovale, and it's a hole in the heart that 25% of people have. And if you have bubbles on the venous side, it can cross over and cause type 2 DCS. So we added a criteria for the so-called grade 4 venous gas emboli. Anyhow, I don't want to bore you with all this, but we finally developed these criteria where we could only accept a protocol for use if the DCS was less than 15% and the grade 4 VGE was less than 20% at 95% confidence interval. And then we would reject anything at 70% confidence interval because I didn't want to do a long trial and either accept or reject. So anyway, we got all this peer reviewed. We did these trials. So we did 10 minutes of vigorous exercise on cycloergometry and arm ergometry, 2 hours of oxygen preview, not 4, like we showed, only 2. We were non-ambulatory for 4 hours before the flight. We designed a suit simulator where we had bungee cords attached to us and we had a fake foot restraint and we had all the tasks that matched the metabolic rates. So the first test that we did was phase 1, which was 2-hour pre-breathe, 10 minutes of exercise and this non-ambulation. And we got 19% decompression. Then in phase 2, I knew that there was exercise associated with getting into the suit. And so we modeled that, we measured the MET rates. And so we added just 40 minutes of light exercise. And for those that might be physiology, this is really low. It's 5.8 milliliters per kilogram a minute. I'm doing that right now as I talk to you. You know, we added that light exercise and we got no DCS and really low grade 4 VGE. I could talk to you afterwards about the theory about why that worked. But anyhow, so we accepted that and we did some more trials. And I was assigned to do the first spacewalk from space station using this protocol. And so we went up and we installed the airlock. And then this is me for the first time doing the exercise pre-breathe protocol. I'm on an oxygen mask. You're already in your LCVG and you're exercising. And then after that, we actually go to 10.2 PSI and break pre-breathe and don the suit. And then here we are going out the door in this little thing called the crew lock. So there's 2 astronauts and a bunch of other crap that you're taking out. Not much room. And oh, hang on, I should have done that differently. Let's see, does this go over there? Anyhow, it shows me going out the hatch. And in the shuttle, when you go out the hatch, there's a payload bay underneath you, so you feel like there's a floor. But on space station, the hatch is pointing nadir, so you look out and you feel like you're falling from 245 miles. That's a little well, this is a tour through space station. The Russian part of the space station has like this Velcro everywhere. It reminds me a lot of the Jules Verne Lodge that we were doing. I mean, this is what they call the FGB, where they stow a bunch of stuff. So here I am floating.
So you just pull yourself along.
Yeah, you just push yourself. If you're good, you can just glide. There's the airlock real quick. Going through the lab. So it's really cool to float around in space. So after that mission, I had always wanted to be an aquanaut, like live in an underwater habitat. So I was a commercial diver, did all the stuff I just told you about. So I was lucky enough to be part of the NEMO missions, and NEMO 1, where we saturated in the aquarius habitat, and we do all these kind of cool things that you could do underwater. And that was a great experience. And it was so different than commercial diving, because in commercial diving, you're getting into the diving bell, you run through those checklists. In Aquarius, you're living underwater, you look out the window, there's fish coming by, And it's really a totally different experience. That's an Evo 1 crew. And then we had 2 Habtechs who are always my heroes. Hank is here today, one of the best. And they know that habitat inside and out. And we actually just do our task and missions and don't really attend to the Hab. But actually on the first mission, you might not even know this, Hank, we had flooded a camera, and one of the Habtechs was named Otter, and he was trying to dry it out with a hairdryer, and then he had to go do something else. So he handed it to me. And I'm running this hair dryer, and it's so humid in the entry lock that it shorted out. It just had all this smoke. So we had to put pure fill in and do all that. So it's really kind of a good training experience. So we actually use these Nemo missions to get a sense of how somebody can do in space. And if they can't handle it, it's good to know it now rather than once they get to space. So that's a cool habitat. There's the galley. Oh, there's always a big grouper that was coming up the window, like actually a Goliath grouper is probably 200 pounds. So one of the problems is spacesuits, and I led this whole project called the EVA Physiology System and Performance Project. So if you look at the Apollo guys, we looked at all their tapes, and 2% of the time they were either falling down or getting up from falling down. And it was because of bad CG. So underwater was a good place to do this. So I started this research program where we had this pogo system that offloads you to be like 1/6 gravity. And this is not going to play. I gotta do it now. So everything we did, we first did shirt sleeve. So here we're walking at various speeds, and this is all shirt sleeve. And then we do it again in the suit to understand what the metabolic and biomechanical cost of the suit was. And I don't want to get too detailed, but here's a plot of the VO2. That's the amount of oxygen you're burning as a function of speed. And the blue line is Earth, like no gravity, 1G to shirt sleeve. This pink line is lunar gravity, where you weigh like 60 pounds, but no suit. And then the orange line is where we weight matched you. So we actually had you weigh the same thing as you would be in a suit, but you weren't in the suit. And then the green line is the suit. I've got lots of subjects in here. So the metabolic cost of the suit is about 15 milliliters per kilogram minute, which is a lot. And in fact, if you look at Mars, I don't want to bore you with this, but there's the metabolic cost of the suit. And if you try to go fast on Mars, your met rates go through the roof. And so we need lighter suits or another way to do EVA that we're about to get into. So here's some Nemo missions. We built this CG rig, and you could do all these different tasks with different CGs. On the right, we did those same tasks in a neutral buoyancy lab, but with time series motion data collection and a force plate. And with that, you can calculate what's called the inverse dynamics to understand the torque across each of your joints.
And CG is?
Oh, I'm sorry, center of gravity.
Thank you.
So based on that, we made all these recommendations, and the new suit is going to have a better center of gravity. So the challenges of doing planetary EVA, one of the biggest things, people don't know this, is the solar protons. Apollo 15, that crew would have died had they launched 10 days later. And so that's a big deal. These long duration missions we're planning were 3 8-hour EVAs per week. EVA is extra vehicle activity. The Apollo suits were only used 3 times. Apollo had an unpressurized rover, but with that, your range is limited to the range you can walk back if the rover failed. And then we actually couldn't go to 100% oxygen because of the Apollo fire. So I led the development of what we call the exploration atmosphere, which is 8.2 psi and 34% oxygen. So you're already undersaturated compared to 1G. So the suit, as someone was asking me, it tears you up. And as you close your fingers, you have to generate so much tip force that you occlude the blood flow. So you get ischemic tissue damage, and then the bladder pulls your veils off. And as you do all this ambulation, you get blisters. And I always say it's an honor, but not a pleasure to do a spacewalk. So as we're getting ready to build the space station, there was this thing called the wall of EVA, where we were going to do more EVA in about 5 years than we had in all of NASA's previous history. So as we started the lunar program, I coined what we call the mountain of EVA. So here's the wall of EVA, and now we're going to do all these spacewalks on the moon. So it's clear to me we needed a paradigm shift with how we do spacewalks. And so at the time, all these mission planners were assuming you'd have one large rover with 4 crew and an airlock. And if you think about that, if I'm out 100 kilometers and my axle breaks, I'm dead. So I decided to break it into 2 smaller pressurized rovers that had this exploration atmosphere at 8.2 psi, 30% oxygen. That enabled us to do these things that I led the development of called suit ports. So instead of going out of an airlock, you open a hatch and then you step into the suit. And then the inner hatch closes when you press a button. And now all I have to do is depressurize that small vestibule between the hatch and the flip. So I save tons of gas, and then I keep all the dust outside. So we did this. The other thing in the ceiling, I have 500 pounds of water, which absorbs the solar protons, but we also let that freeze and it becomes a fusible heat sink, so that during the day when all your systems are operating, it can melt the ice. And so you don't need to have a deployable radiator, which would not work well with the dynamic driving loads. So anyhow, so we had this concept and we did a prototype of this like really fast. This took like a year. This is Gen 1, it got better, but I wanted it to be luxurious. So we picked these synthetic leathers that were really comfortable. We had the front seats pulled down so you could have a bunk. We had great windows so you could make observations from inside as well as you could, or probably better than in a suit. Here's the sleep curtain that pulled down, and there's a material in there called visqueen that suppresses sound. And so you have your own little room for 8 hours a day, which is really good. And even on the Aquarius habitat, they don't have that. And I did a mission with Scott Kelly, and that dude snores a lot. Yeah, it's like 3 or 4 days before I could actually get to sleep. So anyhow, we built this thing. We took it out in the desert, we tested it, and we compared it to our performance in an unpressurized rover. There it is. There's the suit ports. Here's a little video. You can drive sideways in this rover, sort of cool. There's my coffee cup. So we're sitting there talking about where we want to sample, and we made much better decisions. And then when you want to sample, you go to the suit ports and you get in the suit and you're out the door in like 12 minutes.
Wow.
It averages 11 minutes and 17 seconds. And so you're walking around this big heavy suit, and then so these EVAs were short. We would go out for 25 or 30 minutes instead of 8 hours. And then you come back in, have a cup of coffee or lunch or whatever, drive to the next site, go out again. So it's really kind of a game changer. And so we built this, and then we did Nemo 14. Hank was involved, and these guys are my heroes, but they actually, to my design, built the lander that we were going to use. So this is dimensionally all correct. So we built this lander, and we wanted to offload the rover. And when the lander was actually 18 feet high, and if you fall from 18 feet on the moon, it can break your suit. So we had to use all this fall protection equipment and understand how that worked. There we are with the rover, and we evaluated different CGs and incapacitated crew. How would you get them back inside the rover? It was really good. It really exploited the advantages of the underwater environment, because you weighed out at 1/6 gravity. You don't have a string on your back holding you up. So we learned a ton. We published lots of reports out of this. There's an incapacitated crew that we brought up with a davit. And then shifting gears, and I put it right on time. The next thing we started looking at was, could we work on an asteroid or Phobos, the moon of Mars? And so Phobos, people don't know this, but it's a moon of Mars. And this is John Young jumping on the moon, and he goes up about maybe 4 feet. On Phobos, if you jumped, you would go up 1,000 feet, and it would take almost 12 minutes to go up and come back down. So now you don't have the advances of microgravity where you can float, and you'd have all this dirt and dust. And so we started looking at how would I work there? And the simplest thing was a jetpack, but on Phobos, there's 2 points called the sub and anti-Mars point. And at those points, the gravity is so low that you could almost achieve escape velocity. And the orbital mechanics were very complicated. And I said, I don't want to be in a suit and end up on an escape trajectory. So we went to my rover design, the same rover we had for the moon, and we put hopper legs on it so we could hop off the ground. We worked with the astronaut on the arm. And this whole thing weighed about 7 pounds, but with 7 pounds, you can do a lot of tasks. And if we had to put a lot of force, you could fire the up-firing jets that would force the rover down. So we built this whole high fidelity sim of all this. And then we did Nemo 16, which was probably the most complex Aquarius mission ever done. So we had these submarines, single person, we had a foot restraint on it to sort of simulate the task that we would do with my rover. And we evaluated all these different tools, and it turned out that is the way to work on an asteroid. So that was really fun. Here's a little simulation. And so the idea is that you would hop off with your legs to get on the ground and fire the jets. And it turns out on Phobos, there's these monoliths that nobody knows what they are. They're like 40 meters tall. And, and Mars is like 8,000 kilometers away. So it's right in the background. Just imagine this. It's right out of science fiction. And the truth is, it is so much easier to go to Phobos than to land on Mars. And so I think when we actually go to Mars, we'll probably go to Phobos first. So I spent 2 years designing this whole mission. It was really fun. Oh, I'm going to get off the stage with a couple things. My mentor was a guy named Dr. Lambertson, who is the founder of the SEAL team. He invented the oxygen rebreather. It was pulled out of medical school to work for the OSS in World War II. And he started this Institute for Environmental Medicine at University of Pennsylvania. That's where I developed my dynamics model and did all these tables and stuff. And so this is him. And when I first met him, he was probably about my age. He looked old, so maybe I don't know. He looked very professorial. And then when I went to shake his hand, it was like, okay, it was like a bear trap. They were like, okay, there's something more going on here. But some of his things, he'd say, what do you need to do? Now, how do you do it safely? Not what can I do safely? So if we need to explore the moon or Mars, we got to go. That's it. We do it. Now, how do you do it safely? And it used to always say, do it sensibly. And in today's world, you get all this complex stuff. And, if it doesn't make sense, it's no good. And then physiologically, I always said, measure big things so you can learn something. And then the other one that really stuck in my mind is that models are tools to help you think, not to stop you from thinking. So that's a big one. Then the last thing he said, don't let the bastards get you down. There's always people that will try to, suppress you. Anyhow, this is.
You're good. You're great.
Yeah, this is my literally turning it over to questions. But on my first spacewalk, I had this task that I didn't realize how special it was. But we had people get frostbite in the vacuum chambers, and so for 20 minutes, my only job was to go up on the robot arm above the payload bay on the shuttle with all the lights out and try these glove heaters to see if my hands would get cold. And so I'm just up there. And actually, one of my feet wasn't totally in the foot restraint, so I wasn't moving at all because I didn't want to fall off. But at night, it was, and you could see Jupiter and its 4 moons with your naked eye. And the Milky Way, a lot of you guys have been in the middle of the ocean. It's probably 10 times brighter. And then I remember looking down, I could see a fine line of white light on the wing of the shuttle, and then a crescent of blue as the Earth is rising. And then for like 25 seconds, you're hanging there between day and night, and the ocean permeates out into deep space. And we came out on the day side over Hurricane Maryland. And I remember being overcome with a deep sense of pride, not for myself, but for this whole team at NASA that had the technology to put me up there above the hurricane. And then the radio clicked on and said, okay, now back to work. Anyhow, there's me done in 38 minutes. Okay. Okay, so fire away with questions. Yes, ma'am.
I have a question. You were talking about PFO.
Mhm.
And I would have thought that you would really test for that. I mean, I just started applying for a a job and they're like, oh, I hear something, you've been told you, and I have to get an echocardiogram.
Yeah.
So I got this, just a diving job.
Yeah.
And it's like, no, I've never been told that.
Yeah.
And they tested.
Well, they shouldn't. So where we ended up on that is you should have a decompression procedure that's so safe that even if you have a PFO, you don't get bent. And there was a lady named Dr. Julie Swain that was trying to get us to screen astronauts for PFO. And I fought it, and the data showed that we didn't need to do that. And so our policy is don't screen for PSO, don't leave them off. If someone gets a type 2 hit, then look at it. And if you have a PFO, then look at closing it or changing your diving habits.
It's nice to know I don't have, but it's like,
Yeah, yeah,
never even thought that it would be.
yeah. And the commercial industry does not screen for PFO unless you have a type 2 hit. So that's the right posture, because otherwise you're eliminating people for the job, or you're picking somebody to do a spacewalk just because they don't have a PFO and they can't hit their ass with both hands. So
So if we have a question from the audience, if we could restate it for
okay.
the people on YouTube so that they can hear
sure.
and then answer, please.
Okay. Can do
Thank
that.
you.
Okay, so some other, just
So I was just curious. So I don't have the best ears.
mhm,
I had tubes in my ears. So for me to get down, it's a little hard.
mhm.
On the commercial side, like what was the average depth you were doing?
Oh, I
Is
did
that
all kinds of
possible?
stuff. I did surface diving actually to 420 feet out of a bell.
So the question was,
So the question was, what was the average depth of my commercial diving career? And it varied. We did a lot of shallow water stuff, which is really hard when you're because the pressure changes more as you get near the surface. So I probably, I don't know, probably had 300 hours at 300 feet plus, and another 400 hours at 60, 70 feet, 400 dives rather. So you need good ears. You need to clear. And afrin's always nice, but don't overuse it. Yeah. Okay. Yes, sir.
Actually, I have like 10 questions.
Okay.
I'd like to boil it down to two.
Okay.
Up on slide 30,
Uh-huh.
you went by an item that to me is very important. That was waste management.
Oh, yeah. Yeah.
So as a professional diver,
Mhm.
if you're in a wetsuit,
Yeah.
you go.
Go for it. Yeah.
I happen to have been on both shuttle recovery jobs in
Okay.
96 and 2003. 96 was easy because of where it was. 2003 was in Toledo Bend in Texas in
Yeah.
February.
That was nasty.
Okay, and we wore dry suits. Okay, our dives
Yeah.
were over an hour long.
Mhm.
You spoke of excursions that were 8 hours.
Yeah,
long. Okay, tell us about.
Yeah. So,
Waste management.
so you start out life.
What was the question?
Oh, the question was, how's waste management done in a suit, probably? So you start out life with diapers, and then you end up as an astronaut, you wear diapers. And so we had these things called mags that were really like lots of pads. And so we also drink water from a water bag during the suit. And so you would urinate a lot. And the humidity separators of the suit would dry that diaper out. So when you come back, it was completely dry.
So you're telling me you peed on yourself?
Oh, yeah.
oh,
Yeah. Well, in a funny story, so these things work great in space, but we were doing these tests at Duke and other universities. And I sent them up these diapers to use because we didn't want them to ambulate while they were doing the exposure. And the diapers leak in 1G. So that was a big fuss.
And I'm sorry to just jump in with the second one. I work with kids.
Uh-huh.
And one of the things that we do is we measure success in small things. And one of your slides, I think 77, it said, measure success in big things.
Well, what Dr. Lemons has said, this is physiologically. So if you want to do a test, do something big. Because if you're measuring small things, the N has to get so high to prove or disprove the hypothesis. So that's not a message for life. That's a message for physiological research. But I would concur with your thought that success can be really small things and they add up to big things. And it's good, it's rewarding when you have success. So it motivates the kids and stuff. So that's cool. So you're obviously a Navy guy then.
I am Navy. I spent 33 years in the Navy, 28 as a Navy diver.
Well, good for you. That's great. Yeah, Yeah, Challenger was nice, clear water in Columbia, that was bad. That was rough, and elder swamps and stuff, yeah. Okay, that's, yes, sir.
So you gotta spend the rest of your life, do you go space or ocean and why?
Okay, good question.
What was the
But-
question?
So the question was, for the rest of your life, would you rather go to space or the ocean? That's a hard question to answer. I love the ocean, I've always loved it. I love what you see and what you feel, all your senses, floating and all that. Space is almost bizarre. But you're out there, it's hard to work in the suits, but you have unlimited visibility. It's like the suit itself and you weigh 600 pounds, so you don't have any weight in space, but you have that mass. And if you start going fast, that inertia keeps going, so you'll flip out of control. And so I would like to go to the moon and try out my rover that I'm now building for a private company. So if I had a choice, I would do that. If I did it just for pleasure, underwater, by far.
Good question.
Senator Rubio has recently sort of moved the UFO phenomenon.
Yeah.
The obscure.
Oh, yeah, yeah.
Into a serious national security issue.
Right.
Unexplained aerial phenomena.
Uh-huh.
There's something there. Have you ever seen when you were in outer
Yeah.
space something that you
Yeah.
can explain? And do you believe in UFOs?
So
What was the question?
the question was, have you ever seen a UFO in space? And the answer is a lot.
Wow.
But it's not what you think. And people would drop a wrench or a bolt or something in the payload bay of the shuttle and they'd lose it on the ground. When you get out into space, we're finding the RCS jets and these things come floating out. And you don't know exactly what it is, but they're floating out. So in terms of aliens, I have to think that as vast as the universe is, that there's intelligent life a lot of places. As far as the physics that we understand, we can't go faster than the speed of light. And so they couldn't get to us unless you have immense energy and can warp space time and do a wormhole. So there's a lot we don't understand about physics, but it all comes down to thermodynamics and energy.
So you're saying there's a chance?
There is a chance. Now, all this stuff that we've seen here, I don't think those are aliens. And there's all kinds of experimental spacecraft, Area 51, drones, weather phenomena. So most of it can be explained. Some of it's kind of hard to explain, but I don't believe that it's alien life, or they probably would have contacted us. Mhm.
When we see photos, when someone's up at the ISS, it
Mhm.
appears to be black. What do you actually see on the planets, of the stars, once you're out of the stratosphere?
Yeah, okay. So the question was, what do you see when you look out in space, like from the space station? And you see this beautiful Earth, this jewel blue Earth, and then it's hanging there in the blackness of space. So it's just, the background is all black.
Why?
Let me think about a good answer for that. So there's no atmosphere and space is essentially infinite. And so, and there's lights, but those are stars and they're billions of light years away. So it's just black.
So when we see a formation in the sky,
Mm-hmm.
Big Dipper,
Mhm.
belt and all, is it the atmosphere that allows us to see that?
No, it's the light traveling from, a million light years or whatever to your eyes. So when you see a star, you're seeing light that came from millions, if not billions of light years. It's kind of hard to fathom, but
But you don't, when you're.
well, I mean, we see the stars much clearer because we don't have the atmosphere. Okay, so there's no atmosphere, and so you don't get glare, for example. Like the sun is like this diamond, and we have a visor, a gold visor, but you don't get glare because there's no atmosphere. And another little backstory, but on my second spacewalk, there was a big scratch in my helmet, like a big honking scratch, and you know, they had already loaded the suits on the shuttle. They said, we'll just go with it. So I was, So I was worried I couldn't see anything. Never saw the scratch because your focal point is past that. So that's something that a lot of people don't appreciate, but you can have the thing all scratched up and you're looking past it. It's really interesting. Okay, so another question.
Oh, I have a couple from online, so people watching from home. The first one is, what was the scariest moment for you when you were in space?
So the question is, what was the scariest moment in space? Probably on my second flight, I was the shift commander of a 24-hour day operation, and we had a fuel cell crossover. And so the fuel cells use liquid oxygen, liquid hydrogen. They combine them in a half cell that generates water and power. And there was starting to be leakage, and if you combine those, it would blow up. And so they called up to do this procedure called fuel cell safety, where you actually close the react valves and do a bunch of stuff. And I did all that, and they didn't close. And then they said, okay. And then we had this other switch on the C3 console that had a switch guard over it. You had to get a screwdriver out, take the switch guard off, and then push a circuit breaker and then fire this pyro that would permanently close the valves. So I woke up the other crew because I wanted 2 eyes on that. Like if I shut the wrong fuel cell down, that was it. And we did that and it didn't close either. And so they went back to bed, and then on the ship, so the ground had me maneuver the shuttle because it's called a solar inertial attitude. So we're getting sun on it because they thought it was frozen. And so in the ensuing 4 hours, the Space Lab computers crashed 9 times. And the long form malfunction is like 45 pages long. So I'm working through all this stuff, and then the KU band went out, and then finally they warmed up and closed. And then we had to do what's called a group B power down, where we power all this stuff down, and we're working with flashlights in our mouth and stuff. And you know, so I wasn't scared because you're trained, and I actually felt like, okay, they got their money's worth out of me because I didn't make any mistakes. And then later I called the ground and said, hey, can I get some chow for the payload crew and turn on the heaters in the cabin? So we did that, and we had to come home early. And it was actually interesting because all of the procedures for entry are written for the first failure. And since we already had a fuel cell failure, we had to redo all of the procedures. So the mission control guys were working overnight. And at the time we had a thing called a TIPS, it's like a fax. And they faxed this thing up. It was probably 100 yards long. And all 7 of us were having to cut and paste that into all the books. It took us 4 hours. Fortunately, we didn't have any malfunctions on it. So that was probably, at the time, they said, other than Challenger, that was the worst failure in the shuttle program. I got to be in the middle of that.
I have one more question from Zoom, and then we can go back to some questions. This person asks, were the fingernail injury photos you showed prior to your use of the Phase 6 glove design?
Very good question. So they asked, with the fingernail picture, damage of fingers prior to Phase 6. Yes, the first series was the Phase 4 gloves. And then we had these Phase 6 gloves that were very good gloves. And I had custom gloves, like $300,000 gloves. And that made it better, but didn't solve all the problems. So I actually had to super glue my nails down and then put these pads in the crotch of the comfort gloves that would oppose the force that we did. So I'm muddled through it, but the folks at ILC, with maybe this person involved, they were great. I mean, they would work so hard to get those gloves right for you. And they actually did a casting of your hands and built the gloves around your hands. And they actually gave me, I have this, my hands on a little flash. So, you know, that just brings up the other point that, you know, when I said I had a sense of pride coming, you know, into the hurricane, that wasn't for me. That was for all of these people all over the country that are doing all this work to enable that to be possible. It's really quite staggering when you think about the number of people having to do everything right. Okay.
Thank you.
Fraser.
Yeah. Tell them the story about, I've heard it, but what's it feel like whenever you're taking off?
Oh yeah, so that's interesting. So you're all strapped in. So the question is, what does it feel like during liftoff? And so you're all strapped in, you go through some procedures and then there's a long hold and you're literally like kind of going to sleep and, just hanging out. And then they call you again for the final switch throws before you launch. And, you're ready for anything. And they light the main engines for 6 seconds to make sure that they work and that they gimbal. And if it passes those checks, then the solid rockets ignite. And there's these frangible bolts. And now you're going up and it's like vibrating like this, and lots of G's, and like you really can't even read the computer screen. So it's very, very intense. And then I showed you that video when the rockets separate, there's a big explosion, and we had that in the sim, but the magnitude was like 100th of what you actually had in space. And on my first flight, it was like, okay, this is it. We can blow up, but you get used to it. But it's a wild ride.
Anyway, yeah, I can serve in the Navy and submarines, and we'd be underwater for 2.5 months at a time.
Oh, cool. Yeah.
And what for you, what was the biggest psychological challenge to stay motivated for the long game?
Yeah, good question. The gentleman was a submariner in the Navy, spent 2.5 months in a submarine. He probably had a little more room than we did. So what made it work for me was to have the attitude of what can I do to make my crewmates' life easier. And if everybody has that attitude, like, hey, can I fish you some food? Hey, I've got a free minute. Can I help you with the procedure? Get 2 sets of eyes on the switch throw. And with that kind of attitude where you're really just trying to help each other, it works really good. And the other thing I always tell kids is look for what you like in people, not for what you don't like. So when you're assigned to a crew, find something that you like about that crew member. And it's so much more fun to work with people that you like. And there's no room for negative energy, like none. And so spaceflight, you have to be your very best to do it. And so you have that kind of attitude. And I'm sure it's like that at diving. And I did the diving. You have to be honest with each other and help each other when you can, so.
Thanks.
I have one more question.
Mhm,
This
yeah.
one's an interesting one. They ask, how did returning to Earth from space feel versus returning to the surface from an Aquanaut mission?
Oh, that's a great question. So
Missing sensations.
the question was, how does it feel returning from space to 1G versus coming out of saturation to the surface? Lots different. Coming out of sat's not a big deal. It's kind of nice because you're not in the little chamber. Coming back from space, you adapt really quick to this microgravity. You're floating around, and when you come back to Earth, you feel like, what is this force? This gravity force is pulling down, and like after my first mission, we went into crew quarters so we could meet our family. We had lunch there, and I was eating a sandwich and talking to my mom, and I was going to use my hand, so I put the sandwich out. And then circle back to the dog thing. So at night, when you want to go to the bathroom, you float out of your sleeping bag and you go over to the bathroom. And so my first night back from space, I got out of my bed and I was crawling on the floor. And then the dog was looking at me like.
Wow. Does anybody have any other questions? And Mike will be around. Go ahead, Amy.
So in the video of you and Jan Koblik,
Mhm.
what year was that?
That was 1995. And we actually it was like a pure coincidence, but it was, well, hello.
That's
You should be on the dog crew. It was at the anniversary of the first link up between Scott Carpenter and C-Lab and Gemini 5. And so we recognized that and took the opportunity to have that link up to highlight the oceans and the similarities between ocean and space and trying to protect our oceans. So it was pretty fun actually to do that.
So if somebody comes to the History of Diving Museum and sees the featured exhibit, they'll see us playing the link up of you on the Endeavor and Jan Koblik and Scott Carpenter inside Jules Undersea
Yeah.
Lab. So,
Yeah, if you listen close, you can hear me answering the questions. It's sort of,
Mhm.
it's taken from the point of view of the habitat versus being the shuttle, but somewhere in the archive proofs, me and the shuttle. So,
But we have to get that from NASA, and we got the other one from Jan.
okay.
There was a little less red tape.
Yeah. For those of you that don't know, Jan Tobuk is one of the early pioneers in underwater saturation diving. You know, he has the Georgia Lodge and he has this great program that educates kids. Like, it's fantastic. And he's a very resourceful guy that knows how to get stuff done and really tries to inspire kids, which, you know, that's kind of like giving back with all this stuff that we got to experience. Let's give it back to the kids. So.
You had one more question?
How does someone qualify to become an astronaut? I mean, is there IQ tests? Is there? Is there personality tests? And I mean, obviously you're brilliant. Is every astronaut brilliant as you? Or is it?
So the selection process is very rigorous and like literally thousands of people apply. And they screen it down into very qualified, which means you know you have the degrees and stuff like that. And they go to highly qualified. And out of the highly qualified, they pick like 100 people to do interviews. And they bring you up to Johnson Space Center for a week. They do every medical test that you can imagine. You do IQ test, personality test. The personality tests are always interesting because they ask you the same freaking question like 20 different ways. And then you get annoyed and they think you're going to say what you really mean. But anyhow, so you do all that. And then the other thing that they don't do anymore is they have this survival sphere. And they put you in there and they'd wire up the EEG and EKG. And it wouldn't tell you how long. So it's pitch black. It's a little beach ball. I mean, you can't move. And I just went to sleep. But some people got panic. So that's like, you know, that's claustrophobic, not good. So.
And some of the missions aren't some of them like, didn't you get picked for one because of your size and your arm reach and a task that needed to get done?
Not really. I'm not bragging, but I was very good at spacewalking because of my commercial diving background. So I got assigned to do all these spacewalks to build a space station. And then I became an instructor astronaut and I trained other astronauts how to do EVA because some of these people are brilliant folks, you know, scientists or pilots, and they've never done this kind of work, right? And so you have to let them learn how to do it and do it their own way. But for these divers, I mean, that was the best training I could have ever had for spacewalks because you have to plan your dive and
Sea legs,
and do what?
your sea legs.
Sea legs.
Yeah, no, I never got seasick. Ever. Actually, we had a diver that was a Navy diver that was, I forget his name, but he was always seasick. I'm in there, man. He did it. He's a good diver.
So if anybody else has any questions, Mike's going to be here for a little bit. You can put them in the Zoom and we'll get back to you. We're going to be recording it while it's recorded. It'll be uploaded tomorrow. So if you're seeing this at another date, we do monitor those and we'll get back to you with the answers. The History of Diving Museum would like to thank you for coming. We have a little gift bag for you. We like to try to go green, so we have a nice reusable.
Okay.
Inside is a membership. I know you're busy, but you could come here 362 days for free.
Well, so the good news is I collect diving helmets, old diving helmets, and this is the best collection I've ever seen. I've been here many times before on email missions. I love this museum. It's actually amazing.
Well, thank you.
Yeah.
And we also have an Aquanauts to Astronauts shirt.
Okay.
It's one of our event shirts, so
Very
you
nice.
can be both an Aquanaut and an astronaut on that
I
shirt.
need some more work. Okay, well, awesome.
So thank you all for being here. Thank you for tuning in. And we invite you, if you're not a member to the History of Diving Museum and support free presentations like this, we invite you to join on your way out. All right. Thank you very much.
Okay, yeah, thank you. Not a good sponsor.